okay, which will be important. Okay, so all of you, when you did your undergraduation, okay, when you talked about determinants and all, okay, you might have come across terms like conjugate transpose and conjugate transpose and only transpose and so on. Okay, so these are some standard symbols that are being followed. Okay, so if you are following any other kind of symbol, you have to just make sure that you are actually consistent. Okay, what I will do is a dagger, I'll just keep it for conjugate transpose. Okay, and a dagger, I'll just keep it for transpose. Okay. One more property that you might remember is that if you just take the transpose of AB, okay, it's nothing but B transpose A transpose. So these things you have already learned, okay, and maybe I can take an example here. If you basically consider any matrix, okay, let's say for any matrix A, right, maybe A is a matrix here, okay? And what we do is we have to prove, let's say, A transpose and A transpose A are symmetric. Okay, they are symmetric. So these kind of sums are usually like basic, which you might have already done. Okay, and then what we do usually is we use this property. So what we can do is probably we can just take it this way: A transpose, and we can take a transpose of that. Okay, so we have it as A transpose of A transpose. Right. So we can just simply write it down as A transpose. Right. So A transpose, and you take the transpose of that. This is A transpose. This is only possible because of this property. Because when we take the transpose within the bracketed term, it gets reversed, right? B comes first, A comes later. But for the second term is A transpose. So you've taken A transpose of A transpose. So it's basically nothing but a property of a symmetric function, right? If it's skew-symmetric, there will be a minus sign there, okay? But it's not there in the particular case, okay? So even for this also you can prove, okay? So these properties you have to again remember, whatever you've done in your undergraduation, that's important, okay? And maybe one more example we can take about Hermitian and skew Hermitian, okay? So what you have to prove is this A plus A dagger, okay? A dagger. And maybe I have one more. Okay, I'll give two more here. A dagger and A dagger A are Hermitian. Okay. And maybe I can give you an example of skew Hermitian is A dagger minus A maybe. Yeah. Okay. Skew Hermitian. So you have to just prove it's Hermitian or skew Hermitian. Okay. So before I proceed, I hope that all of you have done it. Okay, you've done these properties of metrics. Okay, and find out determinants and all. Okay, and when we talk about matrices, you know what are symmetric and what are skew-symmetric, Hermitian and skew Hermitian. So this may be another example that you may need to practice. So whatever question I'm giving here, you basically just need to practice it. Okay, that's very important. If you just practice, probably you can just recall everything. Okay, very important in mathematical physics to recall. And if you look into the syllabus, this is more or less nothing but a repetition of whatever you have done in which is there in the first unit. Okay, of course, some of the topics are there which are new. We'll be doing it. Okay, so if you want to just prove it to be Hermitian, you have to just take the conjugate transpose. Okay, so you just take A dagger plus A dagger. So conjugate transpose is actually the matrix itself. So it is A dagger plus A. So it is a commutative relation. We know that. We can just simply write it down as A plus A dagger. Okay. So that means the conjugate transpose of A plus A dagger is A plus A dagger itself, right? So that means this is nothing but Hermitian. Okay. So in this way we usually do it, if you remember. and then you can do the other two also, right? But when you are taking basically this, you have to just reverse it and do it. Okay, so it should not be a problem. And then you have got a dagger minus a. Okay, so remember, you can just take the conjugate transpose of this. Simply put it as a dagger, then dagger minus a dagger, right? So this is a minus a dagger. So we can just take a minus sign out, and this would be again the original one, which is a dagger minus a. So this is minus of the original form that we had, a dagger minus a. That means this is information. Okay. So you sometimes get it. You might have done it in your UG. Sometimes you get a problem where basically just directly they will give you a row matrix. Okay, they will give you a 3 by 3 matrix or a 2 by 2 matrix, and then ask you show that it's Hermitian or skew Hermitian. Okay, so practicing those sums back will actually help you out to do better. Okay, I think you can always do it. It's not very complicated. Okay, okay. Let's just recall some more problems. Okay. Maybe I can just type this sum and give it to you and see if you can recall this. Oh, okay. We just do it in this way. So something like the rank of the matrix and all these things also needs to be remembered. Okay. Today we will try to do as many numerical problem on whatever you've done. Okay, as many possible. Okay. So A is equal to, let me just take this. The matrix is 1, 2, 3, minus 5. Okay, this is there. And you have to modify A adjoint of A is equal to adjoint of A into A is equal to determinant of A into R. Okay. So this is something which you have to verify, and if you remember, this is actually a theorem. Okay, and in your UG, I think that is important. But then anyway, we will do a capsule course on this revision. So probably within 2 days, we'll learn a lot of things or learn a lot of things. Okay, so I'll give it to matrices and you have to just find out the rank. This is one. Yes. 2, 2, 5, 2, 4, 3, 2, and 3, 3 or 5. Number 4. So when you are actually in a class, and sometimes you see that, oh my god, I don't remember this, how do I do this, I forgot, I did not practice, and so on. Okay, so these realizations should be there, so that like even if you're not able to do it, you'll just go back and actually have a look and try to recall whatever you've done in your earlier classes, okay, junior classes, and that is what will actually help you to practice better. Okay? That's, I always prefer doing that, okay, sometimes. Usually do is I consider the column number and the row number. Okay, for example, in this particular case, this is the first row, this is the first row, this is the first column, this is the second column, this is the second row, this is the first column, this is the second row, this is the second column, right? Basically what happens, it is I plus j, right? This is the sign convention, if you all recall. And then when you want to write down the sign for a particular element, okay, for the position of an element, we basically just take it to be minus 1 to the power I plus c. Okay, so I hope you all remember this. So if I take this, it is 1 plus 1, 2, so minus 1 square, even square, so this will be plus 1, okay. So when you take the cofactor, you can just take this up, this will be nothing but minus 5 and so on, okay. So you keep doing it, and then that's the cofactor that you design, and if you don't recall, you really have to practice, okay, important. But then the second one would be, second step is actually just to take the transpose of that. So if you just take the cofactor and take the transpose of that, you basically get your adjoint of A. Okay, so do that. Then you have to just do this matrix multiplication. Okay, again, this is something which you should recall. Okay, so column with row, row with column and all multiplication, and you do that, you get this term. Okay, you do the reverse one, you are also going to get a similar term, and then this will be nothing but A. You should take the determinant of that and with the identity matrix. Okay, so this is what you have to do, and I hope now if you can remember this. Okay, so this is important. So okay, so this is sorry, 1 0 0 1, right, and so on. So practice similar sums. Okay, this is 2 by 2. You can practice 3 by 3 and so on. Now I am telling you this is also important because even in your NetGet exams also they still ask these questions. Okay, what these might have done in an undergraduation, it is there in the syllabus. Okay, so even if you are not doing it, we need it. Okay, so that's very important. Okay, so just maybe provide one more sum. Okay. Okay, I can actually give you to find out inverse, I guess. Okay, but before inverse, I'll just show you one sum here. So mathematical physics is all about practice, practice, and practice. Okay, that's very important. And before we proceed, maybe we can just talk about characteristic root and characteristic vectors. Okay, so this is something which you may have done in quantum mechanics and all. Okay, but in the concept or the idea basically comes from mathematical physics. Okay, so maybe we can just do this. Okay, let's start with something which is more important. Yeah. Okay, so we're going to discuss about characteristic roots and characteristic vectors. Vectors. So basically you can have a non-zero vector, okay, and this will be actually associated with a matrix, and then you can actually have something which we call as characteristic root and characteristic vector. We also call them as the eigenvalues and the eigenroots. Okay, so eigenvalues are very important even in quantum mechanics. Okay, so maybe I can write it this way: a non-zero vector x, okay, is defined as a characteristic vector, okay, of a first matrix A. The term square is important here, okay. If there exists a number lambda, okay, I'll write it down such that, okay. So maybe I can use my pen. Here it is lambda, okay. And characteristic root and vectors, we are going to do some sums now, okay. Ax is equal to lambda x, okay. So if you can write it down in this way, okay, we actually can get the characteristic and the characteristic vector, okay. So what are the different terms here? If you go by this definition that we just had, this A is basically a square matrix, okay, first thing. This A is a square matrix. Okay, and then X is the characteristic vector. Okay, so there are different names here, but then characteristic vector or eigen vector, something which is more popularly used. Okay, then we have got the characteristic group. Now X you have already defined, so this lambda is the characteristic group. So what happens is we are going to solve some problems here, and then we are going to see characteristic root. Okay, or we can say the eigenvalue. So eigenvalue and eigenvector is something which you actually come across a lot of times in quantum mechanics, and maybe it's out of the scope of the quantum mechanics syllabus to explain it. There maybe the term would be used again and again, and you are supposed to know this from mathematical physics. Okay, so this is where we are really looking into it. So we have got a square matrix, okay, and we have got an eigenvector. We multiply with it. It should be equivalent to a eigenvalue, okay, multiplied with that same characteristic vector. Okay, but then this is something which is mathematically defined. If you just do a sum, maybe it will be more clear to us. Okay, so let me just have a look at the sum. Okay, let me give you one sum for this. We will do one sum, and then we can get and look into some theorems associated with it. Okay. So let's take one example. We have to find eigenvalue and vector, or eigenvector and eigenvalue. And if we just write the matrix, given matrix is A is equal to, this is 1, 2, 3, 0, 2, 3, and 0, 0, 2, 0, 0. We have to find out the eigenvector and the eigenvalue for this particular matrix. Okay, so how you usually do or proceed with this kind of problem is you have to basically just take A minus lambda I, A minus lambda I is equal to 0. Okay, so when you write down in this particular form, okay, you can actually take this I to be the identity matrix and take the original matrix there and take A minus lambda I. You basically get a matrix where you can take the determinant of this, okay, this matrix, the identity matrix, okay, and lambda, it's actually nothing but the eigenvalue. The aim is to actually find out the eigenvalue in this particular case. So if you take the determinant of this, you can solve it and find out the value of lambda. It's a 3 by 3 matrix. You are going to get 3 values of lambda, okay, and if you get those 3 values, those will actually represent eigenvalues. Okay, so once you get the eigenvalues, you can actually find out the eigenvectors. Okay, so for eigenvectors, we can just do it this way: Ax is equal to the first value that you get, lambda 1x eigenvector. So you see here, if you look into this particular form of the equation, if you write it down as Ax is equal to lambda x, the first thing is to find out the eigenvalue, which you can find out using this metric representation. Okay, find out the determinant, solve for lambda. Once you get a value of lambda, you can write down the equation Ax is equal to the 1x. Okay, and
Hello,
then you
sir.
solve it and find it out. Yeah.
Sir, lambda values are 1, 2, and 2.
Okay, one, 2, and 2. So there are basically three values that you get. Lambda 1 is equal to 1, lambda 2 is equal to 2, and lambda 3 is equal to 2. Okay, so this is a simpler sum. If you basically just take up the determinant form, you'll straight away see that it's easy to actually determine the values of lambda. Okay, and then what you can do, you can take up this Ax is equal to lambda 1 into x. Okay, and try solving it. Okay, so I'd like all of you to just do it. Okay, this is not done yet because she has told the answer, but all of you have to do it. If once you do it, and then we will proceed. Okay, all of you are here. Okay, so I'll ask randomly that who has done it and who has not done it. Okay, those who have done it can relax. Those who have not done it, do it. Okay, we have two different characteristic group. Okay, it basically cannot correspond to a single characteristic vector. That's again important. Right? So um, for this, even the proof is a bit important. Okay, uh, two different groups cannot correspond to a characteristic vector. Okay, so this I want to prove it. Okay. So if I just want to prove it, it's not complicated. Okay, we can just say, let's say, okay, there are one vector x and it basically has got two characteristic groups, lambda 1 and lambda 2, let's say. Okay, so if we do that, in general, what we can say is, let's consider the contrary, right? Let's consider the contrary. Okay. So in contrary, it means that like lambda 1, lambda 2 correspond to lambda x, right? So that lambda 1 and lambda 2, okay, uh, correspond to matrix X. So that means we can just simply write it down as Ax is equal to lambda 1 into x, and Ax is equal to lambda 2 into x, right? And in general, if we just this is I just both is Ax, so if I just subtract it, let's say if I just subtract one from the other, then we simply write it down as Ax minus Ax is equal to lambda 1 into x minus lambda 2 into x, which is lambda 1 minus lambda 1 minus lambda 2. Okay. This lambda 1 minus lambda 2 into x is equal to 0, right? Because this is ax minus ax, so that's 0, right? So it obviously says that since x cannot be 0, if x is 0, you don't have the vector, yeah, okay? So x cannot be 0, therefore both the Eigen vectors are the same. Okay. So these small sums, there are one or two marks. We can always practice along. Okay. So that is going to actually help us. Okay. Okay. Let's just get back to that problem and let's just do it in a bit of detail so that everyone gets it. Okay. Because sometimes it does happen that you may not have done it, but if you have done it, you are not expressing yourself. It will happen. And that's quite obvious. Okay. Not a problem. What I will do is I will just do this. Okay, so this is for all of you just to follow the steps. Okay, so suppose you are given a matrix. I have taken a simple example. You sometimes do get a lot of complicated matrix. Okay, and so on. You get a third order equation, and then you have to solve it. Okay, and then so on. So these things you have to just sort it out on your own. Just try to think contracted with it. But in general, when we actually do these kind of sums, okay, what we do usually is this. We have to find out the eigenvalue and the eigenvector. The first step is actually to find out this A minus lambda I is equal to 0. Okay. So I'm assuming that at least some of you might not have done it. Okay. And I think it's okay to assume that because sometimes we tend to forget things. Depends on which class you've done this part of mathematical physics. So 3. So I hope you understand this. Okay. I is basically an identity matrix. For those who don't remember, okay, it's 10 to the power of 1, 0, 0, 0, 1, 0, 0, 0, 1. So the diagonal elements are 1 here, okay, and then we can just take up to the a minus lambda I. So just subtract the diagonal elements, okay. So this will be 0, and then this will be a minus lambda I guess, this is 3, and then we can take the 0, 0, and then this is again 2 minus lambda. So the equation needs to be satisfied. It should be equal to 0. Okay. And if you do that, you can just see the first term here is 1 minus lambda. Okay. And then you take this and this. Okay. And a bit more detail for the first term. This is 3, this is 0, this is again 2 minus lambda. Okay. Okay. And then plus. Okay. Or we can just take it to the minus if you remember determinant. First row, first column, plus, and then this is your first row, second column, so it is minus. Let's look at this to minus. And then we have got this, and so this is 3, 0, 0, 2 minus lambda. So everything will more or less become 0. 0, 0, 0, 2 minus lambda. Okay, this is the second term, and then we've got the third term, so let me just do 3 plus 3. Okay, and then I take this, if again is going to be 0, you can see. So this is a simpler sum. Okay, this is basically an upper triangular matrix form. You have all the lower terms below the leading diagonal to be 0. Okay, 0 and 0. So this is going to be 0 if you take the determinant. This is going to be 0 if you take the determinant. Okay, so this left out with 1 minus lambda, and you take here 2 minus lambda, 2 minus lambda, this is 3 into 0, 0, right? So this will be 2 minus lambda, 2 minus lambda is equal to 2. So from here we can say that since all of these are independent, so each of them is equivalent to 0, we can say lambda is equal to 1, 2, and 3. So this is actually how you find out the eigenvalues, okay? And this is one part, and if you get a question on this, maybe anywhere in general, you get around the marks divided between eigenvalue and eigenvector, right? So let's say for we want to find out this for lambda is equal to lambda 1, okay? And we have got lambda is equal to lambda 2 is equal to lambda 3. They are unique in its own nature, so the value is the same. It is something. Okay. So my energy is a bit low here today, so please bear with me. But it's important. Mathematical physics, easier thing is that if I do more sums on screen, this is much more helpful than me talking. So for the first one, what you can do is you can write down ax1 is equal to x1 lambda 1. Okay, let me write down lambda 1. And lambda 1 is 1, right? Lambda 1 is 1 here. So this is a lambda 1, lambda 2, lambda 3. So lambda 1 is 1, so I can just simply write it down as ax1 is equal to x1. Okay. And then what you can do is you can probably use whatever you're comfortable with. Okay, you can write down that column thing, or you can just go for x, y, and so on. Okay, but I think it's better to write it in this way. So you can just write down these vectors 1, 2, 3, and then you can write down 0, 2, 3, and then you can take it to 0, 0, 2, okay. And then you can write down the vectors here. So x, this is the first column, second row first column, third row first column, right? So this is the form of the vector that I should get. And then we have got x1 here, we are going to say this x1, 1, second row first column, third row first column, right? We have this. Now what we can do is we can actually try solving this, okay? So first row of this, the first column of this is how we multiply these vectors, okay? Matrix form. So if you take this 1 into x11 is x11, and then 2 into x21 is equal to plus, I can just write it 2 x21 plus 3 times x3. Okay, so this is equal to the first element of the matrix. So it's x1. Okay, so this is 1. And then the second one, I can just write it to be this is 0. So x11 is 0, corresponds to 0. 2x21, 2x21 plus 3x31, right? This one and this one. 3x31 is equal to x3. So this is there, and then the final one is this 0 multiplied with this 0 multiplied with this. We got this and this. So you can write it down as 2x1 equal to x3, right? So if you just do this one, if you solve it, right, you can just take x31 minus x31 is equal to 0, right? So what you can do is you can just take that x31 is equal to 0. You can compute from here. x31 is equal to 0. So this vector is 0 here, okay? So this is there. And then similarly, you can do it for x21 also. x31 is 0, right? So this is 0. So not arranging it that much because it's very simple here. x21 plus 0. Okay, this is the first conclusion that we have. And then we can put here, this one is x21. So from here it can be concluded that x21 is also equal to 0. So that means we have got x31 is 0,
Hello,
x21,
sir.
yeah.
So I have found a mistake for the lambda one here in our case,
Yes,
where
yes.
where we were getting the 000 matrix, but here
Mhm.
we must get the 100 matrix as a result. That means
Correct.
the vector for the eigenvalue 1 will be
Mhm.
100
Mhm.
column
Right.
matrix.
Yes, yes. Okay. So that I was saying that there seems to be some kind of metric. Okay. So plus you can have in general what happens is if you basically have a vector x. Now for any value of x11, okay, you'll basically get x21 and x31 is equal to 0. Okay. So for any value of x1, okay, you can just do this. Value of x11, okay. We are going to do one more sum where you'll see that probably or not. I'll check that. I think we have it. Okay, I have one sum where we can see that all these three won't correspond to 0. For any value of x11, x21 and x31 is equal to 0. Now you have to just think about it that everything cannot be 0 here. It's not a piece of 0 vector. Okay? Everything cannot be 0 here. So if you just look into this particular equation, okay, you basically have a corresponding value when x21 and x31 are equivalent to 0. Okay, because you can just look into a matrix form and try to understand that. Okay, so if we just basically take it in this way, in general what happens is we can say that thus for any value of x1 then, okay? So that means we will just take this to be x1 and when you're finding out the first vector here, x1, okay, is equal to, usually it is written in this way for any values I'll just put a constant c, okay, c is equal to 0, okay, and c is a constant, c is a constant, okay, so we can choose c to be 1, let's say. So a vector form which is actually valid for lambda 1 is equal to 1 is x1 is equal to 1, 0, 0. So this is how we do it. Okay, so you'll see that finding out the eigenvalue doesn't take that much time, but then solving this will actually take some time. Okay, so this is actually important. So if you just go for the remaining values, okay, you see for 2 you get ax is equal to lambda 2x. So lambda 2 is my 2, to be 2 times of x. Okay, and if you do it in general, okay, um, okay, 1, 2, 3, 0, 2, 3, 0, 0, 2.
Hello, sir.
Yeah,
For the previous case, the eigenvector will be a row vector or a column vector. So I
it
think
will
it
be,
will be a column vector, na?
oh, it will be a column vector, right? Yeah, 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 it will be a column vector. So yeah, we can a row vector. Right? Yeah, 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 sorry, sorry. This is a column vector, right? This is the form that we have here. 1, 0, 2. We're going to get this column vectors, okay? X, Y, Z, maybe. I'll just write it down as X, Y, Z for this particular case. Okay, so if you just do it, okay, we can just solve this. Okay, so the first one would be, I think, x plus 2y plus 3z, okay, is equal to 2x. This one. The second one, this x is 0, so it is 2y plus 3z is equal to 2y. Okay, and the third one is 2z is equal to 2z. Okay. So it turns out to be in such a way that basically this is quite obvious, right? Left hand side and right hand side should be equal. These are 0, 0, this is 2z. So when you do this calculation, the final term this should also be 2z. This also tells you that whatever eigenvalue you have calculated is actually correct, this particular step. Okay. So this will actually correspond to z is equal to 0. Right? And if you just put z is equal to 0, let's say here, okay, you get the value of y also, but then here x, if you put z is equal to 0 here, okay, you just get that. If you just solve it, okay, let's just try solving this. What is the value of x that you are getting? What is the relation between x and y? Z is equal to 0, that we know, okay.
So in place of 2y plus 3z, we can put 2y only
In
in the first equation.
this one, right? So just write it down as x plus 2y is equal to 2x, okay. So in general, if you do it, 2x minus x is x, so x is equal to 2. So we have these two relations, and these two relations are okay for actually finding out the values, okay. So we should have it in such a way that x is equal to 2y and z is equal to 0. Okay. So you know x is basically an eigenvector of a corresponding to this values, right? So what we can do is we can write it in this way: x2 is equal to x3, both corresponds to the same eigenvalue, is equal to, so x is equal to 2y. So if we take y to be c, we consider this y to be every arbitrary constant c, then x, sorry, it's not x, is equal to 2c, right? So x will be 2c. Z is equal to 0. Already found it out, right? So if you just take for it, it's for any arbitrary constant, okay? So in general, when we write it down in the exam, we just write it down for any arbitrary constant. C, right? So therefore, if C is equal to 1, you can just simply write it down the vectors to be x2 is equal to x3 is equal to this is 2c, so that's 2, 1, c. Okay. So those who have done it, it's fine, but those who have not done it, please note this down, okay? I don't mind taking the screenshot, but my handwriting is not good. Even if you take a screenshot, you should be clear that what exactly is written there, okay? So let's practice some more sums on this, okay? And I've taken this problem, maybe I have not solved it. Let's see if we can do it now, okay? Here also we have to find out the eigenvalue and the eigenvectors and determine the eigenvalue and eigenvector of the matrix, okay? So the matrix is 0, 1, 0, 1, 0, 0. And this time I want everyone should do it since I told you the steps in detail. 0. Okay. You have to find out the eigenvalue and an eigenvector. Eigenvalue and then eigenvector. Okay. Eigenvector. It's actually simple, it's not very complicated.
So the eigenvalues, I got the eigenvalues.
Yeah.
0, I and minus I.
0, I and minus I.
Yes.
So see it's imaginary value.
Sir?
I means imaginary.
Yes, sir. Minus 1 root over minus 1.
Root over minus 1. Okay. Others do. Let's see. Let's see what others get. Okay.
Sir, eigenvalues are 0, 1 and minus 1.
Yeah. If you answer that means one of you is wrong. 0, 1 and minus.
Yes, sir.
Let's see for answer. And then you can find out the corresponding eigenvectors.
Hello.
Yeah.
0, 1, minus 1. My answer was wrong. 0, I minus 1. That was wrong.
Hello, sir.
Yeah.
Sir,
Yeah.
and the eigenvalues are 0, 1 and minus 1.
Yeah. 0, 1 and minus 1. And then you can find out the eigenvectors also. It should not be very difficult. I think it should be 1 minus 1, 0, something like that. Okay. So you can find out the eigenvalue and eigenvector. Okay, let me give you one more for practice. to not here it's equation where we are getting all three values to be different values. No, then it want two values in 2 1 1 1 3 1 and then 1 2 2. So in general, what I will do is we will like starting from now we'll be doing some theorems and all those things. But as far as numerical is concerned, we'll practice 2 or 3. Okay, before that I'll take one and solve it, and then I'll give it to 3, and then you have to do it. Okay, so that I'm just clear that everyone understands it, and then everyone can practice. The mathematical physics, more or less practice and practice. The properties of determinant, properties of matrices, okay, and then how do you exactly use vectors and matrices command, and these things we might have done, and it's important that you try to remember that. Okay. Yes, yes.
So I got the eigenvectors. So for eigenvalue 0, the eigenvector is 0 0 0, and for eigenvalue 1 it is 1 1 0, and for -1 -1 1 0.
Sir, we have to normalize the vectors also here.
Yes. We have
So
to normalize
according to that, it has to be for lambda is equals to 1, it has to be 1 under root 110.
1 under root 110 means you mean 1 under
1,
root
1 by under root 2,
yeah.
110.
Okay.
Yes, and for lambda is equals to -1, it is
Okay.
1 by under root 2 minus 1 by under root 2 and 0.
Okay. So let me just write down the vectors here. There will be a column matrix and a row matrix. Draw that one. Row or column.
Sorry, sir, you're not audible.
Am I audible? Hello?
Yes, sir.
Yeah. So will it be a row matrix or a column matrix?
Column matrix, sir.
Okay. And what are the vectors you are getting? Vijita, you can first.
Yes, for lambda is equals to 0, all are 0.
Yes.
For lambda is equals for lambda is equals to 1, it is 1 by under root 2, 1 by under root 2 and 0.
0.
And for lambda is equals to -1, it is 1 by under root 2, minus 1 by under root 2 and 0.
So this is actually the answer. You basically have to normalize it. Okay. Basically, normalizing is again important. You have to just take out whatever vectors you're getting, and then you take the square root of that and add them up. Okay, and then you get that normalized vector. Okay. So what I will do is I'll probably leave this as homework for all of you.
Sir,
Yeah, all those are
sir,
done.
for lambda,
Yeah.
sir, for lambda equal to 0, I got 0 0 1, and for lambda equal to 1,
I
I
still
got.
did not. I still did not get the answer, but then since I'm leaving it for homework, tomorrow let's see how many of you get it, and then based on this, not tomorrow, Monday, we'll decide that okay, which one is correct and which one is wrong. Okay. So
Sir, is the normalization is really needed here?
yes,
Otherwise, we.
yes. Actually, you see, basically you have to verify the orthogonality, right, of the eigenvector.
Yes, sir.
Well, when we write down these expressions, we actually have to write down the final vector in the normalized form. Okay? So,
So but we didn't do that in the previous question, like the
yeah,
2
we
1
did not.
0.
Yeah, because I was just introducing that. Okay, but this one we can actually normalize. So what happens is sometimes you get a field to the question, verify the orthogonality of its eigenvectors, right? So when such questions are given, try to normalize into it. But sometimes, it depends on the mark. But I would suggest that you can actually normalize also. Okay. But even if you don't normalize it and if it is not asked, then mark is okay, justify marks. Okay, but
So
then
if I do, so if in the question the orthogonality is not asked, then uh, should we proceed for the orthogon for the normalization process?
no, no.
Or
As I said, no. If even if it's not asked, you are not normalized, you get your mark. Not a problem.
so, sir, in this question the orthogonality has not also asked, and
No, no.
that's why.
It may be asked. Okay, that's what I'm saying. Maybe a tail to the question. Let's verify the orthogonality of its eigenvalue. Then it will just
Yes,
give that.
but for
Okay.
normal question we can write the normally the
Yes,
vectors,
yes,
no?
yes. Even if you don't
Okay,
normalize, you just write it down. Then also it's fine. Okay. This is also
okay,
fine.
okay.
That is not a problem. Okay. But then we'll just leave it to you for now. I'll see that everyone does it. Okay. Because all of us have got different pace of learning. This one also I have to give it as a homework, and you can try doing it. Okay. One more practice that I'd like to give you is okay. It's there. Let's go. Yeah, this is again for all of you. Okay, this is also something which is needed to be practiced, and something which we are doing, we have already done it in our previous classes. So, but then it needs to be recalled. It's very important. Inverse of the matrix. Inverse of the matrix also. If you know it, it's fine. But then, so if you don't remember it, please recall and practice it. Okay, take out your old books, check what you have done there, and then do it. Maybe I can just give you this one example here. So minus 1, 1, 2, 1, 3, 4, 0. Okay. So all of you please practice this under the inverse of the matrix. Okay. If you do it once, it should be easy. Okay. You basically find out the adjoint of A and divide it by this is the formula. So that's your inputs. Okay. And if you do it, this is the answer that you should get. I'm just giving this for practice. Okay. You will write it down in point 4, point 4 minus point 2. Point I hope you understand. If you take the determinant of this, is going to be 10. Okay, so it's basically like that. Or maybe we will write it down as minus point 2 minus point 2. This is not a homework. This is just for practice. Okay, you practice it on your own, and you can just minus. So practice these kind of sums. It's important for you. And one more is if you remember Pauli's matrices. Okay, Pauli matrices. This is again something which you'll be using in your quantum mechanics. Okay, Pauli matrices, spin matrices. Okay, and there you have to prove that these are some sums that you should actually know. Is equal to the integer matrix, and then sigma I, sigma j. These are all coming from this unit of net transition determinants that we are talking. Okay, this I, sigma k. Okay, and then one more is sigma I, sigma k. Okay, plus sigma j, sigma I, sigma j, sigma I is equal to 2 delta ij into the RGB. Delta into the RGB. So this is actually something which is very common even in your NetGate exams also. Okay, so this is something which you can actually recall and practice. Okay, maybe ask you. Okay? when we do mathematical physics, time flies very down around almost 1 hour 20 minutes plus. So we will stop here, okay, today. Tomorrow on the next class we are going to do a theorem which is called Cayley-Hamilton theorem, okay. So once we do the first unit and second unit onward, it will be more newer topics, okay.